All right, so now we move on to lesson 4 of Unit A, and it's graphing non-uniform motion, aka accelerated motion. So in the past couple lessons, we've started establishing the idea of speed. We've talked a little bit about velocity, distance, displacement. We've now established all that terminology that goes with it. But now instead of just purely looking at uniform motion or looking at constant speeds or constant velocities, now what we're going to do is look at it in terms of how do we graph these if we're now talking about accelerated motion. So let's jump right into it. On the first slide here, suppose we look at this graph and we wanted to talk about instantaneous velocity. Well, instantaneous velocity, what we would say is, let's just track it at any given point. So suppose I was at 10 meters of position and that was 1 second of time passes. Well, what we would do is to calculate the slope at that individual point, we would say we've gone over by 10 and then we have some amount that we've gone for 1 second. So my slope would therefore be equal to 10 meters over 1 second, and we would therefore say, okay, this is 10 meters per second. That's what our velocity would be, or whatever our speed is. So because this says position, I'm going to assume this is talking about a velocity, and there we go. And we could consider this also, because it's a positive slope, positive 10. Now, the question that gets proposed right at the bottom is they say, is the instantaneous velocity the same as the average velocity? And the short answer to this is yes. And the reason is because suppose I'm considering this position, or even this position, or even this position. Well, if you realize it's going to be 30 over 3, 20 over 2, even 40 over 4, this will always result in 10 meters per second. And so no matter if I take the slope at an individual point, or if I took 2 points and calculated the slope, it would be the same thing. And let's just algebraically show this very quickly. Suppose I took the 0, 0 point and maybe the 30 and the 3. Let's calculate the slope or the velocity of that overall slope, or the line that connects here to here, thus being the average velocity. I look at this and I'm going to say, okay, well, the second position has a y value of 30 meters minus 0 meters, which was the origin point, divided by, we go to 3 seconds, which was the value of time at the second point, minus 0 seconds. Therefore, I get a velocity equal to 30 meters divided by the 3 seconds, which therefore gives me positive 10 meters per second. So there we go. We've proved right away that the instantaneous velocity of 10 is equal to the average velocity on any sort of interval. So yes, this is true. So is it the same? Yes. Okay, now that we have that for linear lines or things that are uniform motion, what if we take a graph that looks slightly different? So instead of being a straight diagonal line, now we get something that is curved. Well, in the case of a curved graph, what we need to recognize is that is the slope going to be the same thing no matter what? And what you could do is you could sample it by drawing different tangencies. So suppose I'm at 4 seconds. I draw the tangent line at 4 seconds. There's what it looks like. Let's say I'm at 14 seconds. So I'm up here. Whoops, a little more in than that, so I'm going to erase that. If I'm at 14 seconds, I'm kind of like right about here. And so what I want to do is I just want to drop it down to where it's on the graph, which would be just slightly lower than that, and then we'll draw our tangency. So at 14 seconds, here's my new line of tangency. Well, clearly, here's what I want you to label, is that if I look at the slope of the following line, the one to the right, versus the slope of the line down here, the slopes are not the same. Now, what's another way of saying that the slopes are not the same? The velocities are not equal. And so you could say velocity 1, which is down here, velocity 2, which is up here, just two random velocities we may calculate. V1 does not equal V2. That's the, or velocity 1, I'm going to say veloc 1 does not equal veloc 2. There we go. So just to put it in more like verbal terms, I know I could write the whole thing, but our page is a little condensed here. So if the slopes are not the same and the velocities therefore are not the same over the whole thing, then we can't assume that the average velocity equals the instantaneous velocity like we could for uniform motion, which was the graph on the previous page. So let's figure out how we can figure out the instantaneous velocity given one of these graphs. In fact, we actually already have the tools and we've discussed these tools, but let's just really formalize it. So when we have a distance versus time, or more importantly, even a distance versus time, displacement versus time, position versus time, you could call this a P versus T graph. That's another way that it's often shown. When a D versus T graph contains acceleration, the instantaneous velocity does not equal the average velocity. Very, very critical point here. So anytime there's accelerated motion, the instantaneous at any given moment will not be the same. So now here's what we're going to do. We're going to take that same graph that was on the previous page and say, well, suppose I wanted to figure out the instantaneous velocity at 10 seconds. How would I do that? Well, let's take a look. So what we want to do is, first of all, we want to draw a line of tangency, or a tangent line at 10 seconds. We're then going to find the slope of this line, and therefore we're going to find our instantaneous velocity. Now, a really critical point before we move on and actually calculate it is this is an approximate method. The reason it's an approximation, not a guaranteed method, is because the guaranteed method actually involves calculus. So you could even write that in here below. We use calculus in order to solve. And are we at Math 31 yet? And I'll even put in the tag of it. Math 31, that's our calculus course. That's a grade 12 course. You typically take it in the last semester. Right now, a lot of you are either in your grade 12 year and haven't got to calculus yet, or you're in your grade 11 year and you're not even close to calculus yet. So right now, we're just going to use this approximation method, which is finding the tangent line, or using a line of tangency. Okay, so let's actually do that here. At 10 seconds, hopefully that dot is drawn for you. What I would like us to do is I want us to draw a line of tangency through that point. And what it's going to look like is the following. And we may have to redraw it, but let's try it out here. That's pretty good. I'll take that. So if you look at this, what is happening here is it's only crossing exactly one time. And I'm going to write that as a note here. If I draw an arrow here, it's only crossing here at the one point. There we go. Only crossing exactly at the one point, and then it extends infinitely in both directions. Now, you could truncate it just like I did here, or you could just keep drawing it outwards as far as you wanted. As long as you can get 2 points off that line of tangency, we're doing good. So what we're going to do is we're going to take maybe this point, and I'm going to try and just force that one to be right there. Realistically, it should cross through there, but we're going to try and force it a little bit. And then I'm going to take this point right here. Now, if I actually label these points in terms of what they are, well, first of all, this first point on the very left, if we're going from 0 to 5 and there's 5 between them, we know that the y value is going to be 1. And in terms of, if we know that this is 6 and this is 8, that means that between 6 and 8, there has to be 5 positions. That means they're separated by a 0.4. So I'm going to make this 6.4 and 1 in terms of the y value, or 6.4 seconds for every 1 meter. I believe we're in meters. Yes, position in terms of a meter. Now, I'm going to go over to this other side here and say, well, where am I? If I know that the 12 line is here and there's a separation of 5 units between those two and they're a 0.4 each, that means I'm going to be at 12.8. So 12.8 for the seconds. And then in terms of vertical height, it looks like it's on the bold line. That bold line is connected to 10 seconds. And I apologize for them being slightly off. That's just sometimes the way that these things print. So we go 12.8 and 10 meters in terms of height. Perfect. Okay, we have 2 points on this line of tangency, meaning we can approximate, or we can give an approximation for the slope at that given point, which represents the instantaneous velocity. So let's actually do that here. If I do that calculation, let's just double check. I think I have it on. Yeah, perfect. We got the work. We got a spot for it on this next page here. If we're calculating a position over time, that is another way of saying we're calculating the velocity at that point. So I'm going to say velocity at 10 seconds, or V10, is equal to, and now what we have to do is separate in terms of position. We're going to say it's going to be position 1, which was, or position 2, I should say. That was our 12.8 minus 6.4, which was the position in terms of our first point. So 12.8 minus 6.4. And make sure we include our units, 12.8 meters minus 6.4 meters. Then divided by, we're going to go back and figure out what are our time values for these. So time value at the other one, which was, and I just realized I'm doing these opposite. Let's make sure I do this correctly here. The y values have to be our meters. So it's going to be actually 10 meters minus 1 meter. 10 meters minus 1 meter, because I got to put my y values in the numerator. Remember, if I do this in terms of a formula, it's going to be the change in the displacement. Let's make sure I got this here. Change in displacement divided by the change in time. So I got to make sure that y value is in the numerator. Now I go back and say, okay, well, in terms of change in time, this is going to be 12.8 seconds minus 6.4 seconds. Now let's just make sure all these values are right on the previous page. So I go back here and I see, okay, we're at 10 seconds. We have a height of 10 on the second one. We have a height of 1 on our first point. We have 12.8 seconds on the one, 6.4 on the other. So now, if I go back here and do the calculation, let's just simplify this very slightly. So I'm going to get velocity at 10 seconds is equal to 9 meters divided by what this breaks down to in the denominator is, well, 12 minus 6 is 6. 8 minus 4 is going to be 4. So we end up getting that this is actually 6.4 seconds. Now, before we move past this, what I'm going to do is I'm just going to type this into the calculator just to get an exact figure, because this is going to probably work out to some sort of decimal. So we get 9 divided by 6.4. This is going to give us a velocity of positive 1.4. And if we wanted to round it to the nearest hundredth, we could put this to 4.1, and this is going to be meters per second. Perfect. Now, because this is an approximation, is this guaranteed to be the right answer? Definitely not. No, it might actually be a little bit different. But what we do want to recognize is that this is a really good approximation without formalizing it with calculus. Now, the only other thing I'm going to add here is, because we're talking about displacements or position, I'm going to add a positive and a positive. And then I'm going to add a positive here because the net displacement was positive. And there we go. That's where we get that positive, or which realistically, remember, we've talked about this. It could mean up, it could mean east, it could mean, like, there's a bunch of different meanings for this. Up, east, we could talk about it in terms of being right. There's a bunch of ways to describe a positive without them actually telling us. We're just going to use positive in here because we're just going to say that we don't know the specific direction. All we know is that it's moving in whatever the positive direction is. All right. Now, in terms of our interactive assignment, here's what we're going to do. I'm going to want you to create a displacement versus time graph, calculate the instantaneous velocity at a couple different times, so 1, 3, and 5. Then take that information and create a velocity versus time graph using those velocities. Finally, calculate the average acceleration and then make an acceleration time graph. Okay, here's what we're going to do. We are going to take these in terms of an ordered pair. 5 and 1, 8 and 2, 9 and 3, 8 and 4, 5 and 5, 0 and 6. Because displacement is always represented by the y, I'm going to put a y here. Because time is always on our x-axis, I'm going to put x here. And now what I'm going to do is I'm going to go back and forwards between this slide and put these on the grid that would make up our displacement versus time graph on the next slide. So 0, 0, and then 5 and 1. So we go 0, 0, that's going to be our first point, and I'll do them in blue. Then we go to 5 and 1, 5 being our, in terms of our position, so we got to go up to 5, which is about midway through there, and then about 1, so we get about here, because we got to go between 4 and 6, which actually puts us just slightly lower. So there we go. We're going to be right about, I just want to make sure I get it exactly between there. There we go. Because remember, these are slightly offset, so 6 and 4, they're on the bold lines there, so just make sure they're connected there. Now I'm going to go back and get 2 more points here. So we have 8 and 2 and 9 and 3. So 8 and 2, 2 is here, 8 is up here. Then we go to 3, which puts us at 9, and that's kind of right in the middle. So I'm going to put it right here. Let's get another 2 points here. We have 8 and 4, 5 and 5. So 8 and 4, which would put us right about here. And I actually got to drop this other point because it's not on the bold line. There we go. There's 2 and 8. We have the 4 and 8, and then our next point was 5 and 5, so I'm going to go down to 5, which is about here. I'm going to go to the bold line, which is here. There we go. And then let's plot our last point, which is 0 and 6. So 0 and 6 puts us right here. And again, remember, the bold lines or the thicker lines are where these times are actually supposed to line up to. So I know it's a little bit distracting, but that's where these are connected to. Anytime you see the bold line, that's where you have to put those. So I'm just drawing like little hashes representing where they're actually supposed to be guided to. Okay, now what I want us to do is connect these with a line. So what I'm going to do is I'm going to connect it through, try to just draw a line that represents this nice parabolic shape or this nice symmetrical arch. There we go. Excellent. Now, what we have to do is we want to calculate instantaneous velocities at the following positions, and I'm going to highlight them. We want to figure out at time 1, what is the instantaneous velocity, time 3, and lastly, time 5. So at each of these, we need to figure out the slopes. So doing that, when we draw these out, let's see if we can approximate what these will end up being. So I'm going to draw a line of tangencies on each of these, and I'm maybe do it in red. So I have my first tangency, which might look like something like that. I mean, not super accurate, but you know, we'll do the trick. Then I'm going to go right to the top here and draw another tangency. So I'm going to just draw it directly horizontal like this because it's at the peak or our maximum. And then lastly, I'm going to go down to the other side here and try and draw one as best as possible. And you know what? That actually looks pretty good. They're never going to be 100% accurate. Remember, we're talking about approximates, not guarantees. So let's actually figure out what these points are. I'm going to go put a point here, and I'm going to put a point maybe here. Okay, actually putting the coordinates for these, if these things range from 0 to 1 and there's 5 positions between them and I go over 3, that means this is going to be 0.6 seconds. And maybe I'll actually do this in a slightly thinner marker here just so that it's a little bit better. So in this one here, I'm going to have 0.6 for the time. And then in terms of the height, if we're going from 2 to 4 and there's 5 gaps between there, that means I'm going to go 2.4, 2.8, 3.2, 3.6 would be my value here. So 3.6 in terms of vertical height. I go to the next one, and this dot looks like it's 1 past 1. So it's going to be 1.2. And then in terms of vertical height, it's going to be right on 6. So that keeps our job easy. What I want us to be aware of is before we do the slopes, we're just going to put all the points. On this top one, right away, I just want you to say the velocity for number 2, this one is going to be 0 meters per second. Why? Because it's a horizontal line, and horizontal lines have a slope of 0. And so it's not that they're undefined, it's that point in which it changes from a positive slope to a negative or a negative to a positive. We get that changeover of this velocity. And so from here, I just want you to indicate that if you realize it's your maximum, I'm fine with you putting 0 meters per second, unless it specifically asks you to show 2 points of tangency and go that way. But for our case, if I see that this is the maximum and it's a horizontal line, that's totally fine to do. Okay, now let's pick out 2 points on our other side here before we do our slope calculations. So I'm going to look at this one here and say, maybe right about here would be perfect. And then in terms of another point, why not here? And I know these aren't exact. They're not exact by any means. You try to get them as accurate as possible, but we're going to work with those. Okay, here's what I have on the first one here. So in terms of the overall time, we're 2 ticks past 5. So that's going to put us at 5.4 because they move up by 0.2 each in terms of the x-axis. In terms of the y, we're 1 below 4, meaning we're at 3.6. Okay, perfect. Now, in terms of the other point, we realize we're at a time that is between 4 and 5, I believe. I don't think it's exactly in the middle. In fact, it is at 4.6. because it's 3 ticks away and they each move up by a 0.2. And then in terms of vertical height, it looks like it's 2 above 6, meaning it's 6.4, 6.8. So this one I should get 6.8 for. Okay, let's figure out what the slopes of these are. So calculating the slopes, I'm going to look at this one here and say, for the first one, let's do all the algebra, maybe in the low part of the graph here. So I'm going to say velocity number 1, remember, because we're talking about velocities, not like m's anymore, using that type of notation. Velocity 1 is equal to 6 meters minus 3.6 meters divided by the 1.2 seconds minus 0.6 seconds. Okay, let's figure out what this math ends up working out to in terms of this. Now, again, what I'm going to do is I'm going to include a positive here and a positive out in front of 3.6 because we're talking about displacements. So I just want to be really exact with that and say they're vector quantities. So this must include the signage. Okay, so we know we're going to get a positive velocity just because of the math. I can see it right away. But what we're going to get is, let's evaluate the number. 6 minus the 3.6 is going to give us 2.4. And then 2.4 divided by 0.6 from the denominator, that's going to give us a value of positive 4.0 meters per second. Excellent. There we go. Now, here's what I want you to recognize. When you look at this here, if I have a point that is exactly directly across, and this is a perfect parabola, a nice symmetrical parabola, if it is directly across at the same position, just the opposite side of the curve, what should we expect to see? Well, the correct answer would be that we get the exact same velocity, but what changes? The direction, because it now becomes negative. So let's just do a little predictive writing up here. So what I'm going to do is to say velocity 3, it should end up being negative 4.0 meters per second. But let's confirm that, or even see if it's close. So what I'm going to do is using the math of this and using our points, velocity 3 is equal to, I'm going to take the values. So we have positive 3.6 in terms of position, in meters minus the positive 6.8 meters. Let's hope I have another bit of room there. Perfect. Divided by the times, well, we said it was 5.4 seconds minus the 4.6 seconds. Okay, let's do this math here. So we have 3.6 minus the 6.8, which is going to give us negative 3.2. And then negative 3.2, 4.6, let's just make sure, negative 3.2 divided by 0.8, this gives us, wow, exactly 4. You know, in class, I don't remember it working out that nicely, but perfect. It worked out great for us. There you go. So this is our value for V3. Okay, so we have our velocity 1, we have our velocity 2, and I'm going to highlight that in yellow just because it's one of our solutions. We have velocity 1, velocity 2, velocity 3. And just like I said, because we're at the same position as we follow it across the parabola along that green line, if I'm at the same position, but just on the opposite direction, if this is like a ball being thrown into the air or a football in its trajectory, and it's landing at the exact same position in after a certain amount more time, I should realize this and say, hey, it should be the same velocity, just the opposite direction. What might affect this is if there's anything like air resistance or friction or whatever else that might pop up, but this is great values for us. So on the next page, we've actually done all the algebra here, which is fantastic. What I'm going to do is just plot them into the next slot or put them in where the answers go, and then we'll actually carry that forward. So here's what I mean by that. Correct answer, don't worry, we've already done that. We've drawn in the tangencies just like we were expected to do. Now, in terms of the actual answers, here we go. So for our first one, we got that our velocity 1 was equal to positive 4.0. It was on the way up. It had a positive slope. Right at the top, we said this was 0 meters per second because it was horizontal. It's that transition from up motion to down motion. Now, V5, or the last one, we called these V1, 2, and 3. Realistically, if I was to go back and maybe change up the notation, what I could have done is said V1 second, V3 seconds, V5 seconds. That's totally fine. For our case, I just did 1, 2, 3 because it was our 3 tendencies. So V5 could also be, and I'll just maybe write them in brackets below. We called it V3. We called this one V2. We called that one V1. So just if you want to see them side by side. Okay. So now we have these different velocities over different time intervals. Now what we want to treat those as is ordered pairs, just like we did before. How are we going to do that? Let's lay it out in the following manner. Here's a velocity time graph or a velocity time table. Velocity is going to be on your y, time is going to be on the x-axis. At 1 second, our velocity was positive 4.0. At 3 seconds, we reached our maximum and it was 0. It was in the transition period. Lastly, we got negative 4.0. And this was in meters per second at the 5 seconds. Now, let's plot those points on a graph in terms of this is point 1, this is point 2, this is point 3. Okay, so for the first one, at 1 seconds, we were at positive 4. So I'm going to put us at 1 and 4. And remember, these things are a little bit offset. So if the 1 is seems like it's a little bit off, that's just the way that the graph kind of came out in the notes. We had 3 seconds, which was 0. So that puts our other point here. And then 5, we were down at negative 4 right there. Perfect. Now, the correct way to approach this in terms of finding out the slope of this that will tell us some critical information is we need to realize that it is the line of best fit that helps us connect these and make out the overall average of the data. So in the lab, we actually did a really good job with this. What I want you to do is I want you to take a line of best fit. I'm going to draw it in blue, and you're going to connect these points. And, you know, it may seem very, very linear. That's okay. We're just going to make sure we draw it as best as possible. And I'm going to draw it even a little bit better than that. There we go. Let's say that that's our line of best fit. I'm not saying it's 100% accurate, but, you know, it averages out the data. There's a certain amount of points above, below. You know, it looks to be a decent average. What we're going to do is if we want to figure out the slope of this line, well, what are we actually solving for? We're solving for the acceleration, because as the formula or the second formula on your formula sheet says, if I look for acceleration, it's equal to the change in velocities. So let me erase that piece there. The change in velocity divided by the change in time. Now, what does this mean? What we need to figure out is we need to figure out the overall slope of this line. We're going to choose 2 points that are on this line so that we can calculate the slope. So let's say I use here, and let's say I use, realistically, it can be anywhere, but I'm going to go a little bit wider out. Maybe I say, and I'm trying to pick a point that's like exact for the most part. It doesn't have to be exact, but as exact as it can be. Maybe here. I know it's not exactly on, but we're going to try and use this point here. So let's label these according to their times and their velocities. So in the first point, we look at that one and we see, well, it's between 1 and 2, and it's 3 past 1, meaning this is going to be 1.6 in terms of time for seconds. And then in terms of velocity, it's going to be, it looks like it's 2 past the positive 2, so it's going to be positive 2.8. And there's going to be a reason I put the positive there, because when we're mixing up positive and negative velocities, we want to be really exact with that. Now, in terms of the other one, we're at 3.4, I believe, because we're 2 past the 3. And then in terms of vertical height, we're 2 past 0 in the negative direction, meaning this is going to be negative 1.8. And with this one, and no, not negative 1.8, 0.8, just to be good with that, 0.8. Perfect. Okay, there's our 2 points. Let's use these to calculate our slope here. So knowing that our acceleration equation is the following, and it's on the right-hand side, acceleration, which is equal to the change in velocities. We're going to take point number 2, negative 0.8, minus the positive 2.8, divided by, in the denominator, 3.4 seconds, which is 0.2, minus 1.6 seconds, which is 0.1. Now, the only thing I'm missing on here is the meters per second. I'm going to try to squeak that in right below here. Meters per second, because we should always be including our units. If we're not including our units, that's a really bad thing. So the only reason I didn't include them originally is that I had to kind of squeeze the numbers in here, but you should always be thinking, I got to make sure my units are in everything. And I will take off marks for that if I don't see them. So 0.8 minus another 2.8, that's like adding those two together. I have 2.8. That means I have a total of negative 3.6 in that numerator. So I'm going to say acceleration is equal to negative 3.6 meters per second. There's my units. Divided by, in the denominator, we go 3.4 minus the 1.6. That gives me an answer of 1.8 seconds. Now, taking this, you know the overall magnitude is going to be some sort of possibly double-digit answer, maybe single-digit. I think it's going to be single-digit, though. It will be negative, though, in terms of its direction, just even by the graph. You know, left to right decreasing. This means it has to be negative. Now let's just double-check the magnitude. 3.6 divided by 1.8. This gives me an answer of negative 2.0 meters per second squared. That's the really critical thing, because what I want you to realize is that the seconds come together. When I see that there's a meters per second, that seconds actually drops to the numerator, and by a 10C scale, it joins with this other seconds, and then you end up adding their exponents. So there's our average acceleration for this problem, negative 2.0 meters per second squared. Now, what does this mean? We have uniform acceleration. Not uniform motion, but uniform acceleration, meaning the object is changing with the same amount of velocity change per every given unit of time. That's really critical. Okay, so let's map this on an acceleration versus time graph. Now that we have this overall slope and this acceleration, let's do it. So I look at here, and there's the answer if we want to really see it again. I see this, and we get an acceleration average of negative 2.0 meters per second. How do we graph that? Well, hint, it's a straight horizontal line based on the slope we found, because we see that the acceleration isn't changing over time. The average tells us that it's changing in velocity per given unit of time by 2 meters per second squared. So what we're going to do is we're going to look at this and say, to draw out our line, it's as simple as the following. We go down to 2 on the graph, we extend it out, and we want to extend it out exactly how much time there was going on in the problem. So realistically, if we backpedal this just very slightly, our time looks like it ends at about 6 seconds. And based on that one, we can actually even go back further. And we found that our last point on the graph was down here at 6 and 0. So we're actually going to use that as the ending time, because that's when it encountered 0 position. So I'm going to go back here and say, rather than just extending out that line infinitely, we stop exactly at 6. Perfect. This looks great. If I extended the acceleration any further, we'd be saying it's accelerating past position 0. That only happens if the position went negative. But for now, because it stopped there and they didn't talk about any further motion past 6 seconds, you're going to want to write acceleration to 6 seconds and then stop it. And what you could do as well is you could draw up a vertical line from here and draw it directly horizontal at 0. This says the following. We travel at an acceleration of negative 2.0 meters per second squared for that 6 seconds. And then after the 6 seconds, the object no longer accelerates. In fact, we don't know anything about the motion. So I'll highlight the part that's optional. This is completely optional. This part in blue, maybe I'll make it green actually. This part is completely optional in the case of this problem because we just don't know enough to further the motion or even talk about further the motion. So we're just going to end it at 6. The green part is completely optional. All right, now if we look at this one here, assuming the previous scenario that we've talked about in class before, a ball is rolling up an inclined plane and it's rolling back down from where it's starting at. Why do we have uniform negative acceleration during that entire time interval? Well, I'm just going to break it down in the following way, and I highly encourage you to do this too. Suppose that I have the following triangles, and we're going to draw out 2 different scenarios. Here is the first triangle, or here's the first ramp, I should say, and here is the second ramp. Now, on this ramp, what we're going to do is, or just off to the side of it, I should even say, is I'm going to draw an index that talks about what the direction of motion is in terms of positive or negative. We've established that the axis is negative is down, positive is up the ramp. And this is going to be really critical. So please include that feature where we're talking about direction of motion and what sign it is, because we really need to be clear with vector values if it's positive or negative. Now, in terms of this graph here, here's what we're going to do. We're going to start up with the going up the incline to start. So I'm going to draw a ball at the bottom, and I'm going to draw an arrow indicating that this is going up the incline. Well, the velocity, and you can draw this with a dotted line, is heading up in the positive direction. Velocity is positive. Because we're heading up the incline, it must follow the convention that up is positive. But what is happening? It's actually slowing down. By the time that it reaches the top of the ramp, we know that at the very top, this is 0 meters per second. It's that transition point where it eventually wants to roll back down, meaning there's something acting against this motion. And here's what it is. We have a negative acceleration, aka the object is experiencing gravity acting against this object. So when these things are going against each other, the velocity in one direction, the acceleration in the other, we can actually classify this and say it's slowing down. And I'll even write that in the box here. It's slowing down. And I'll even put quotations around it because that's what it means for this opposite case scenario where we have velocity in one direction, acceleration in the other. Now let's talk about it when it's at the very top of the ramp. So I'm going to get back my red pen here. I'm going to circle this and then say, what if we want to talk about the object on the way down? Well, here's what we have. In terms of velocity, we know that the velocity is heading in the negative direction. So I'm going to put V negative. There we go. And then in terms of the acceleration, if I bring back my green pen here, what we're going to notice is that the acceleration is going in the same direction as that velocity. So maybe I get this velocity out of the way just so I can reposition that. So negative velocity, there we go. Now that creates a space for me to talk about the acceleration. Acceleration, because it's facing gravity, is in the negative direction still. What does this mean overall? Well, because the velocity and the acceleration are both traveling uniformly well, I shouldn't say uniformly, but they're both traveling in the same direction. What this means is that if they run tangent to each other or they run simultaneous to each other in the same direction, it means the object is speeding up. So in brackets here, or in quotations, I'm going to talk about this object as speeding up. Or you could talk about it as like gaining velocity if you really wanted to, gaining in terms of its magnitude. So we have slowing down, it reaches the top. Once it reaches the top, it hits 0. And then from that 0, it now heads the other way. And because the velocity and acceleration go together down the ramp, we know this is speeding up. Now, please do not confuse negative with speeding up and positive with speeding up. The signs are directional. That has nothing to do with speeding up or slowing down. What has to do with speeding up or slowing down is, are they going in the same direction or different direction? And you can clearly see in both of these cases, one has it where they're opposite, one has it where they're together. These, for all it would have mattered, is they could have both been positive. That still would have meant it's speeding up because why? Both of them are traveling in the same direction. But according to our orientation, we said that negative was going down. So therefore, if they're both negative and they're both going the same direction, aka the negative direction, it's speeding up. If one of them is going up and the other one is going down, like situation 1, it is slowing down. All right, now consider the following V versus T graph. Find the distance traveled and find the displacement. So we're going to look at a velocity time graph and use areas to help us figure this out. So suppose I give you this graph, velocity versus time. What we have to do is we have to segment this into a bunch of different pieces and then add those pieces together in a specific way that either gives us displacement or gives us the overall distance. So what I would recommend is draw a vertical line right at this exchange, and I want you to say that this is segment 1, this is segment 2. Now, I want you to again draw a vertical line right at this changeover and call this segment 3, this segment 4. Now you're probably thinking like, why did I split it up that way where I have these in terms of 1, 2, 3, 4, and I created these areas in this way? Well, what we want to consider is that this middle line or the zero velocity line is what we're going to consider to be our reference line. The reference line being how much magnitude do we have, either positive or negative away from that do we have, and then how much time are we at that for. So if you look at this, it's from 0 to 10, well, that's 10 meters per second in the positive direction. And then how long am I there? For what looks to be 2 seconds. Therefore, I can figure out an area which represents the overall distance or displacement, depending on the way I look at it. So what we're going to do is let's figure this out in terms of all the areas at the different regions. And so I'll do the positive regions, the negative regions, and then we'll discuss it. So here's what we're going to do. For region number 1, I'm going to put number 1. We're going to figure out that the displacement in region 1 is equal to, well, we said it was velocity times time based on our formula. We have to multiply them to get the area, positive 10 meters per second multiplied by 2 seconds. This gives me a total displacement of 20 meters. Now, for region number 2, we're going to say that displacement of region 2 is equal to, because it's a triangle, it's still facing that same 10 meters per second in terms of the positive velocity. It shares the same height. In terms of its length, it's actually also 2 seconds, but we have to divide it by 2 because it's a triangle. Therefore, we get positive 10 meters. Okay, so we have our positive displacements. Now let's calculate our negative displacements. So for number 3, I'm going to look at this and be like, well, if I look down here, this actually dips down to -5 in terms of its velocity. So -5 is the height or the velocity we're going to use. Displacement number 3 is equal to -5 meters per second multiplied by, it's there from 4 to 5 seconds, so 1 second divided by 2 because it's a triangle. Therefore, I get -2.5, and this is in meters. Lastly, region number 4. I'm going to go displacement in region 4 is equal to, again, it's -5 meters per second. Whoops, I got to make sure I put the per second there. There we go. Multiplied by the time it takes, well, it's there from 5 to 8 seconds, so we consider that a 3-second interval. This gives me -15 meters. Okay, now you're probably thinking, how do we put this all together to summarize a final solution? Here's how we're going to do it. If I was doing these graphs, I would always do them in terms of displacements, meaning the vector quantity, because to do the distances, it's really simple. Ignore the signs, add up all the values. So if I added positive 20, 10, 2.5, 15, and I take all these numbers and I just naturally add them together, that gives me the distance. So I'm going to formalize it below here and say, therefore, the distance total is equal to D1 plus D2 plus D3 plus D4. And therefore, the distance total is equal to, I believe, if I'm doing my math correctly, we get 47.5. And this is meters. The reason there's no sign there is because we can't look at this thing and assign a sign. It's not directional. It's just how much. It's the total scalar quantity. Whereas displacement, here's what we have to do. Displacement total is equal to, and you could say displacement total, or you could say the change in displacement. This is equal to displacement 1 plus displacement 2 plus displacement 3 plus displacement 4. Okay, therefore, when we get this, the change in displacement or the net change in position, that's the way it's defined in our notes, the net change in position from where you start to you end. If I add these things together, I get positive 30 in the positive region, and then I get negative 17 in the other region, 17.5, that's exactly. So if I go 30 minus 17.5, I get 12.5, and that's positive 12.5 because remember, the positives outweigh the negatives in terms of this math. So my overall net change in position or the change in displacement is positive 12.5. I ended up in the positive direction. Now, again, what does that mean? I don't know. That could mean east, it can mean right, it can mean up. There's so many ways to categorize this thing. So what we're going to do is just say, keep it simple. It's just positive for now. And then later down the road, we'll specify it a little more. All right, here's the answers. So just to confirm that we got the right answers, or if you want to see them even more formalized than this, again, you see anytime you have a triangle, you have to multiply it by 1/2 or divide it by 2. But other than that, all our work should be the exact same. The only thing they're missing in this solution is the negative right here. Okay, now the take-home points. Let's cover these. A curve d versus t represents acceleration. So on that front page, remember when we went from a linear graph to something that had a little bit of a curve, the instantaneous velocity does not equal the average velocity. To approximate the instantaneous speed, we use the velocity at that time, or we use the tangency method, which is a pure approximate or an approximation because we do not have calculus yet. To find the slope, we use a tangent line and we find instantaneous speed. So calculate the slope of the line when you draw a tangent point that only crosses through the 1. We then look at this and say, if you have a straight diagonal v versus t, there's uniform acceleration because it's not changing in velocity at a different rate. The velocity is changing at a consistent rate. Uniform acceleration is not the same as uniform motion. Oh, amazing point. We need this one, especially as we move into lesson 5. This is critical, hugely critical. The slope of a v versus t equals acceleration, another great point. We're not going to see a curve v versus t. The reason is because this revolves around calculus. So if you want to write in a note again to yourself, this revolves around calculus, or more specifically, integrals. And we don't have the skills for that, so we don't want to do that. Area between the graph line, aka the bold line, and the x-axis on a v versus t equals the distance and displacements. Really critical for any sort of assessment, including unit tests. And then lastly, the only acceleration time graph you'll see in this course is a straight horizontal line, meaning uniform acceleration. So we never face non-uniform acceleration. That involves skills that are beyond this course. So we're just going to keep it simple to anytime you get acceleration, it's a horizontal line that remains consistent for any given unit of time. All right, now additional resources, don't worry too much about these. I think we've covered a lot. I can make these available if we need to, but as long as you can get the general premises of this lesson where we can now shift from a distance time or displacement time graph to a velocity time graph to an acceleration time graph, that skill is critical. And in fact, during the lab, you've actually shown a really good job of this. So I'm not overly concerned with this, but if you have questions, see me right away because this transition from one graph to the next is critically important.